To a modern engineer, pausing a system for exactly 1 second is as simple as typing a single line of code. This command offers a sense of absolute control, but it is an illusion. It hides the massive physical complexity required to actually move electricity through time, the oscillation, the threshold detection, and the transistor switching happening out of sight. To even read that code, the hardware must follow a rigid physical checklist. It has to power on correctly, start its internal clocks, load firmware, and execute every instruction without a single interruption. Digital engineering is built on this magic box approach, a layer of convenience that only works as long as the physical world underneath behaves perfectly. But in environments where systems operate under immense stress, like a commercial turbine or a medical ventilator, that perfection is never guaranteed. In these moments, digital systems fail in ways that have nothing to do with physical wear. Firmware can have hidden bugs, memory can become corrupted, an operating system can freeze. Even a burst of electromagnetic interference can flip a single bit in a processor's memory, causing a catastrophic hang-up that the software cannot fix itself. The fatal flaw of relying on code in an emergency is the time it takes to process. Waiting for a software interrupt, a data conversion, and a programmed response is often too slow for a critical failure. When software crashes, waiting for code to execute is a lethal risk. The digital abstraction is a tool for convenience, not a final layer of protection. This is where analog electronics becomes critical. These circuits aren't governed by programmed logic, but by the direct, unbending laws of physics. Take a comparator protection circuit. It has no firmware. It simply monitors a power line's physical state. If a voltage spike occurs, it reacts in microseconds. The components trigger a hard disconnect instantly, cutting power before a CPU even registers an error. This instantaneous, physics-driven reaction is why these circuits remain the mandatory defense in nuclear facilities and industrial protection systems. An analog circuit doesn't need to boot up or think. It simply exists and reacts, making it the only thing left standing when the digital logic dies. Even the most advanced computer relies on this reality, because in the physical world, perfect ones and zeros don't actually exist. Deep inside a modern chip, data is just analog voltage fluctuating between thresholds. Zooming into a digital signal reveals sloped, imperfect curves of analog physics. As processors run faster, parasitic capacitance causes these voltages to bleed together, threatening the data structure. At high frequencies, simple circuit board tracks stop carrying pure data and begin acting like volatile transmission lines, reflecting signals and leaking noise into the grounding. There is no such thing as a pure digital problem at high speeds. Eventually, every system degrades back into a problem of analog physics. When a high-speed system fails, the difference between a software-only perspective and an analog perspective becomes obvious. An engineer who only understands the abstraction layer is often stuck. They can swap out hardware modules or rewrite code, but they are blind to the physical root cause of the failure. But an engineer trained in analog principles can trace the physical flow of energy. They can see how a jagged path of current leads to a thermal bottleneck at a single transistor, or recognize the signature of a signal reflection. This depth of understanding changes how an engineer works. While some are limited to what the documentation says a module should do, others are predicting how the hardware will behave before the power is even turned on. In the tech industry, software is built on shifting sand. Frameworks disappear, libraries lose support, and programming languages are replaced in a cycle of obsolescence. Because digital systems rely on these layers of abstraction, basic coding tasks are increasingly being offloaded to AI and automated tools. When the work is defined by logical rules and pre-made libraries, the human element becomes easier to replace. Contrast that with the absolute permanence of analog physics. Ohm's law, capacitance, and magnetic energy behave exactly as they did a century ago. They cannot be abstracted away. Digital code tells a system what to do, but analog intuition explains how the system is physically able to do it. One is a set of instructions, the other is a permanent mastery of reality.